The rifle sat on the test bench under white fluorescent light, its polymer shell the color of charcoal. Oberndorf, West Germany, 1982. The facility was silent except for the ventilation system and the occasional click of measuring tools. An engineer named Helmut adjusted an optical caliper around the weapon's rotating chamber mechanism, documenting clearances to the 100th of a millimeter. The G11 did not look like its contemporaries. There was no wooden stock, no brass cartridges visible in clear magazines, no ejection port on the right side of the receiver. The exterior was sealed, angular, and purposeful. Inside, the mechanism represented something different, not an improvement of existing designs, but a parallel answer to the same problem: how to launch a projectile accurately and reliably. Helmut set down his tools and picked up one of the rectangular cartridges from the tray beside him. It felt dense, slightly waxy. The 4.73 33mm round was a solid block of nitrocellulose propellant with a steel projectile embedded in its front. No brass case, no separate primer. The propellant itself formed the structural body of the ammunition. When it ignited, nothing remained to extract. This was the core concept, and every other feature of the rifle existed to support it. He loaded a 50-round magazine, horizontal, feeding from above, and locked it into place. The magazine's shape was determined by the ammunition's rectangular geometry. Gravity played no role in feeding. Spring pressure pushed rounds into the chamber pathway regardless of the rifle's position. Helmut engaged the charging handle, feeling the first round move into place. The chamber, cylindrical and rotating, accepted the cartridge and sealed shut. On the bench beside the rifle lay a schematic, pages of technical drawings showing the internal mechanism in cross-section. The rotating chamber was central to the design. After each shot, it would turn 90 degrees within the receiver, aligning with the magazine for the next round, while the barrel remained stationary. This allowed sequential firing without removing cases, because there were no cases to remove. But it also meant redesigning the relationship between chamber, barrel, and breech. Helmut had been with the project since 1975, when the caseless concept was still theoretical. 7 years later, the rifle existed as a functioning prototype, but each solution had revealed new challenges. The propellant had to be hard enough to prevent accidental ignition from residual heat, but reliable enough to ignite electronically when required. The chamber had to rotate precisely, without fouling from propellant residue. The burst mechanism had to fire 3 rounds before physical forces could disturb the shooter's aim, achievable only because of the rotating chamber's speed. He locked the test fixture into position and activated the electronic ignition system. The rifle would fire into a ballistic containment unit, its performance measured by sensors. This was not about conflict. This was about proving that 7 interconnected engineering decisions could function as one coherent system. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The conference room in Oberndorf overlooked the Neckar Valley, but no one was watching the view. 12 engineers sat around a table covered with prototypes, test reports, and cost projections. The year was 1976, and Heckler Koch had been awarded the government contract to develop a caseless rifle. The contract was clear: reduce user load weight by 40%, improve hit probability at 300 meters, maintain reliability in field conditions. What it did not specify was how to achieve any of those goals. Gerhard, the project lead, stood at the head of the table. He had worked on the G3 rifle, the company's most successful design, and understood conventional mechanisms intimately. The caseless concept was not conventional. "We've confirmed the ammunition works," he said, gesturing to test data. "Propellant stability is acceptable. Ignition is consistent. But feeding remains problematic." The issue was geometric. Traditional rifles used cylindrical cartridges with tapered cases designed for smooth extraction and feeding. Caseless ammunition was rectangular, maximizing propellant volume while minimizing wasted space. But rectangular objects did not feed smoothly through curved paths. The magazine had to push rounds horizontally into a chamber that needed to rotate. Every angle mattered. An engineer named Stefan proposed the rotating chamber solution. Instead of the chamber remaining fixed and the bolt moving back to remove a case, the chamber itself would rotate after firing, presenting a fresh face to the magazine. The burned propellant would leave ash residue, but the next round would push into a clean section of the chamber. The barrel would remain stationary, preserving the point of aim. The concept was elegant, but it required machining precision beyond typical standards. "We'll need to control heat," another engineer noted. Conventional rifles relied on brass cases to absorb combustion heat and carry it out of the chamber during extraction. Caseless ammunition left all that heat in the barrel and chamber. After sustained firing, residual heat could ignite unfired rounds prematurely, a cook-off. The propellant formula would need to withstand temperatures up to 180 degrees Celsius without igniting spontaneously. Cost projections appeared on the overhead projector. The development timeline stretched to 1985, maybe longer. The authorities wanted a replacement for the G3 by the early 1980s, but the engineering challenges were compounding. Electronic ignition required a power source, a battery in the stock. The rotating chamber required a redesigned gas operation system. The burst mechanism required a timing system faster than any standard rifle. Gerhard circled back to the core question: was the caseless concept worth this level of redesign? The ammunition weight savings were real. A person could carry 500 rounds of caseless 4.73 mm for the same weight as 300 rounds of 7.62 mm NATO. In a defensive scenario against superior numbers, that mattered, but only if the rifle worked reliably in mud, rain, cold, and heat. Only if it could be maintained by users with basic training. Only if it didn't require an advanced degree in mechanical engineering to troubleshoot. The decision was made: proceed with the rotating chamber design, refine the propellant chemistry, and develop a sealed housing to protect the mechanism from environmental contamination. The project had 7 major technical challenges ahead, each dependent on solving the ones before it. This was not modification. This was ground-up engineering, using the caseless ammunition concept as the foundation and building every other system to support it. The mechanism revealed itself in layers. At the testing facility in 1980, engineers had sectioned a prototype G11 to examine the relationship between components. The cutaway sat in a transparent case, each part color-coded to show functional groups. Observers studied it carefully, trying to understand how the rifle worked without the familiar landmarks of a conventional action. The first layer was ammunition. The 4.73 33mm caseless round measured 33 mm in length, rectangular in cross-section. The propellant was a solid block of nitrocellulose-based material, stabilized with additives to resist decomposition under storage and heat. The projectile, a 3.4-gram steel dart with a copper driving band, sat embedded in the forward face. A small cavity at the cartridge's base contained the ignition point, where an electrical current would trigger combustion. No primer cap, no case, just propellant and projectile. The second layer was ignition. A battery in the rifle's stock provided current to an ignition module. When the trigger was pulled, a capacitor discharged through contacts that touched the base of the chambered round. The electrical arc ignited the propellant instantly and uniformly. This eliminated the need for mechanical firing pins, striker springs, and primer sensitivity issues. But it also meant the rifle could not fire without battery power, a dependency that conventional designs avoided. The third layer was the chamber. Cylindrical and approximately 50 millimeters long, it sat within the receiver and was capable of 90-degree rotation. After firing, the chamber rotated a quarter turn, aligning its opening with the magazine above, while the barrel remained fixed. The next round fed into the now empty chamber face. Gas pressure from firing sealed the chamber against the barrel. After rotation, it sealed against the new round. This eliminated extraction and ejection entirely because there was nothing to remove. The fourth layer was the gas system. A small port near the barrel's muzzle tapped propellant gas, directing it through a tube to a piston. The piston drove a cam that rotated the chamber. The timing was critical. The chamber had to rotate after pressure dropped to safe levels, but before the trigger was released for the next shot. The mechanism cycled at 2,000 rounds per minute in burst mode, completing 3 shots in approximately 0.09 seconds, faster than the physical impulse of the firing traveled from the rifle to the user. The fifth layer was recoil management. Because 3 rounds fired before the shooter felt the movement, the rifle remained on target for the entire burst. This dramatically improved hit probability. Engineers calculated that a 3-round burst from the G11 had the same likelihood of hitting a target at 300 meters as a 5-round burst from a conventional rifle. The mechanism achieved this through speed and precision, not through reducing the forces themselves. The sixth layer was the magazine, holding 50 rounds in a horizontal stack. It sat above the receiver and fed rounds downward through a spring-driven follower. The rectangular ammunition allowed tight packing, no wasted space between rounds. The magazine released with a single button press and loaded with the same manual motion as any other detachable magazine. Users did not need to learn a fundamentally different way of handling it. They just loaded a different shape. The seventh layer was integration. The optical sight mounted permanently to the rifle's carrying handle, low and weatherproof. The polymer housing sealed all internal mechanisms from dirt and moisture. The stock housed the battery compartment and the recoil spring assembly. Every component had been designed knowing that the others existed. The rotating chamber dictated the receiver's shape. The caseless ammunition dictated the magazine's geometry. The burst mechanism dictated the gas system's timing. Remove any one element, and the entire concept collapsed. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The test range at Meppen was cold in November 1986. Engineers from Heckler Koch had traveled north to conduct endurance trials under conditions approximating field use. The G11 had passed controlled laboratory tests, but laboratories did not include rain, mud, temperature swings, or the physical stress of repeated handling by individuals unfamiliar with its design. 12 rifles sat in equipment cases, each representing a slightly different version of the rotating chamber mechanism. The observers wanted to see a 1,000-round endurance test without cleaning or maintenance. Conventional rifles could achieve this with proper design, though they accumulated carbon fouling and required lubrication. The G11 had no extraction to clear fouling, but it also had no brass cases to protect the mechanism from propellant residue. Every shot left ash inside the chamber. The first rifle fired smoothly for 300 rounds. Then the rotating chamber began to hesitate between shots, the rotation becoming sluggish. By round 450, it stopped cycling entirely. Disassembly revealed propellant residue building up in the chamber's rotation mechanism, fine particles acting as an abrasive paste. The second rifle failed similarly at 520 rounds. The pattern was consistent across the test group. Gerhard reviewed the data that evening. The rotating chamber worked, but its tolerances were tighter than conventional mechanisms. Propellant residue that would have been ejected with a brass case was instead accumulating inside the sealed receiver. The solution could not be clean it more often. Users in the field could not disassemble a rotating chamber mechanism. The solution had to be built into the design. The engineering team returned to Oberndorf and focused on propellant chemistry. The nitrocellulose formulation left more residue than anticipated. By adjusting the stabilizer compounds and burning rate modifiers, chemists reduced ash production by approximately 30%. They also redesigned the chamber rotation mechanism to include self-cleaning features, shallow spiral grooves that directed residue away from critical surfaces during rotation. These changes required new test cycles. By March 1987, revised prototypes returned to Meppen. The improvements were measurable. Rifles now completed 1,000-round tests with acceptable reliability. Some units reached 500 rounds before showing degraded performance. This was within specification, though still below the 2,000-round threshold the officials preferred. Conventional rifles like the G3 could fire 3,000 rounds between cleanings, but they also weighed more, and their ammunition weighed significantly more. Another test involved temperature extremes. Rifles were frozen to 30 degrees Celsius, then fired immediately. The caseless propellant remained stable, igniting reliably despite the cold. Then rifles were heated to 150 degrees and fired repeatedly to measure the risk of premature ignition. The harder propellant formulation prevented accidental ignition even after sustained automatic fire heated the chamber above 150 degrees. This was a significant achievement. Conventional ammunition might ignite under similar conditions. Accuracy testing confirmed the burst mechanism's effectiveness. At 300 meters, 3-round bursts consistently grouped within a 5-centimeter circle when fired from a fixed rest. This was tighter than most conventional rifles firing single-aimed shots. The mechanical principle was sound. By firing multiple rounds before movement disturbed the aim, the G11 achieved precision through timing rather than through force reduction. But the tests also revealed limitations. The electronic ignition system required battery changes every 1,000 rounds. The sealed housing made field repairs difficult. The rectangular magazines were more expensive to manufacture than stamped steel boxes. And the entire system's complexity meant that training technicians required more time than conventional equipment. By 1988, the G11 was functional, tested, and ready for pre-production evaluation. The authorities conducted field trials with infantry units. Users adapted to the weapon's handling characteristics within days. The weight savings were immediately apparent. They could carry more ammunition for the same load, but the rifle's unfamiliarity and the lack of an established supply chain for caseless ammunition meant adoption would take time. The engineering review in 1989 was not celebratory, but it was definitive. After 21 years of development, the G11 existed as a production-ready design. Heckler Koch had delivered on the contract's technical requirements. But the rifle's existence proved something more fundamental. It demonstrated that caseless ammunition could work if the system around it was built correctly. Gerhard prepared the final briefing for acquisition officers. The presentation focused on the 7 engineering tiers, the layered dependencies that made the G11 possible. Tier 1, he began, is the ammunition itself. The 4.73 33mm caseless round required developing a propellant hard enough to prevent premature ignition, but reliable enough to ignite electronically. This took 6 years of chemistry refinement. Without solving Tier 1, nothing else matters. He advanced to the next slide. Tier 2 is electronic ignition. We eliminated mechanical firing pins and primers, replacing them with a battery and capacitor system. This added weight and complexity, but it also provided consistent ignition regardless of temperature. Tier 2 exists because Tier 1 eliminated the primer pocket. Tier 3 is the rotating chamber. Because there is no case to remove, the chamber rotates within the receiver instead of the bolt moving rearward. This allows a firing rate of 2,000 rounds per minute, which enables Tier 4, the burst mechanism. 3 rounds fire before the impulse reaches the user, improving hit probability by approximately 40% at 300 meters. Tier 4 only works because Tier 3 cycles fast enough. The officers took notes. One asked about maintenance requirements. Tier 5, Gerhard continued, is the sealed housing and integrated systems. The rotating chamber cannot be exposed to environmental contamination, so the entire receiver is sealed. The optical sight mounts permanently above, low and protected. This integration reduces modularity, but increases reliability. Tier 5 protects Tiers 2 through 4. Tier 6 is the magazine system. Rectangular ammunition allows horizontal stacking with minimal wasted space. A 50-round magazine occupies the same volume as a 30-round conventional box, but it requires different manufacturing, stamping and welding techniques specific to this geometry. Tier 6 exists because Tier 1 changed ammunition shape. He paused at the final slide. Tier 7 is the operating system that coordinates everything. Gas operation rotates the chamber. Timing mechanisms control burst fire. The battery powers ignition. The recoil spring absorbs firing energy. Every component depends on every other component functioning correctly. Remove one tier and the system fails. This was the final curiosity. The G11 was not 7 separate innovations. It was one unified concept. Caseless ammunition that required 7 dependent systems to function. Each tier solved a problem created by the previous tier. The rotating chamber existed because there was no extraction. The electronic ignition existed because there was no primer. The sealed housing existed because the rotating chamber could not be exposed. The burst mechanism existed because the rotating chamber could cycle fast enough. The magazine existed because the ammunition was rectangular. The integrated sights existed because there was no ejection port. And the complete operating system existed to coordinate all of these dependencies. An officer asked the inevitable question, was the complexity worth the benefit? Gerhard answered carefully, the ammunition weight savings are real and measurable. The accuracy improvement is significant. The rifle works reliably within its design parameters, but it requires a complete logistics system, ammunition production, training, maintenance infrastructure. It's not a drop-in replacement for old designs. It's a different approach to the same problem. The briefing concluded with production timelines and cost estimates. Limited production would begin immediately. Full adoption would require official approval and budget allocation. The rifle existed, proven and functional. Whether it would become standard issue was no longer an engineering question. The Berlin Wall fell in November 1989, 5 months after the G11 entered limited production. By December, the political landscape that had justified the rifle's development was transforming. East and West Germany began reunification discussions. Defense budgets shifted toward integration costs rather than equipment procurement. The priorities of the state changed overnight. In 1990, the decision came. The G11 program would not proceed to full-scale adoption. The rifle worked, the technology was sound, but the strategic context had changed. Germany no longer faced the scenario that had driven the caseless concept. Outnumbered forces requiring maximum ammunition capacity and hit probability. The assumptions that shaped the rifle's requirements no longer applied. Approximately 1,000 G11 rifles were produced. Some went to testing units. Others remained in storage. A handful reached collectors and museums. The caseless ammunition production line shut down. The logistics infrastructure that would have supported the rifle never fully materialized. By 1995, the program was officially terminated. But the engineering legacy persisted. The G11 proved that caseless ammunition was technically viable. It demonstrated that a rifle could function without extraction, that electronic ignition could be reliable, and that rapid burst fire could improve accuracy through timing. Every technical challenge had been solved. The rifle worked. Engineers who worked on the G11 moved to other projects. Some continued exploring caseless ammunition concepts. Others applied lessons about integrated systems, precision manufacturing, and propellant chemistry to conventional equipment development. The knowledge did not disappear. It diffused through the industry. Decades later, designers still reference the G11 when discussing innovative mechanisms, not as a failure, but as a proof of concept that arrived at the wrong historical moment. The rifle demonstrated that reimagining one component, the ammunition, required reimagining everything else. It showed that complexity could be managed through systematic engineering and that 7 dependent tiers could function reliably if each was designed knowing the others existed. The final curiosity remained relevant. Innovation in design is constrained not just by technology, but by logistics, training, strategic context, and timing. The G11 was technically successful and operationally unneeded. It worked in the laboratory and on the test range, but it required a world that was already changing when the rifle entered production. Museums now display the G11 as a historical artifact, a rifle from an era that ended just as the equipment became ready for service. The polymer housing, the rectangular magazines, the sealed receiver, all of it engineered to solve problems that no longer existed in the same way. But for students of engineering, the G11 offers a different lesson. It demonstrates that revolutionary concepts require revolutionary systems, that you cannot change one fundamental element without addressing every dependency it creates, that 7 engineering tiers can work in harmony if designed as a unified whole, and that sometimes, even when the engineering succeeds, history has moved on. The caseless rifle worked, the world changed, and the engineering knowledge remains, archived in technical papers, preserved in museum displays, and remembered by those who understand that innovation is not just about making something new, it's about making something new that the world needs at the moment it needs it. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.